Well, if we want to hit this gnat with a sledgehammer, instead of just saying what it means, and it's important to know how to use that sledgehammer, not so much for this problem, but for others. So using calculus, acceleration is negative 20 centimeters per second. So we integrate that, we get this function that we understand, I think, completely. We get this for the velocity, right? And of course, this is a velocity is a function of time, so we can be specific and call that v of t, right? And of course, this is our v of 0. That's our initial velocity, assuming that this occurs at t equals 0, and those assumptions are kind of implicit. So we solve this, set this equal to 0, solve it, we get this, which is equal to this. Make sure you understand how the units work. Centimeters per second divided by centimeters per second squared. I'll make a note one last time. Dividing by a fraction, we get centimeters over seconds times seconds squared over centimeters, which equals seconds. And that's why this comes out in seconds. Okay? So right there's a picture. Now, if we have questions about position, we can easily answer them by integrating the velocity function, right? Of course, we have canned equations, okay? Using equations of uniformly accelerated motion.
I like those canned equations.
One of the equation is v equals v naught plus at. Okay? Well, that's the same as this equation that we can easily derive by one simple calculus step. But we want to know those equations so we can pull them out when we need them. And we could have pulled this equation out without having to do this. But it's still easier to know what this means. You can immediately reason this out. You don't need anything more complicated than understanding what acceleration means. It's the rate of change of velocity, so it's change in velocity divided by change in time. Okay? And so we could have written that out too. We could have written it out, okay, acceleration is change in velocity over change in time. That'd be average acceleration, but acceleration's constant here, right? So change in time is delta V over A bar equals negative 30 centimeters per second over negative 20 centimeters per second squared equals 1.5 second. Okay? But there's really no need if you understand the meaning of acceleration. Although it's fine to go through this step, it's fine to do all this because you need to be able to do it, right? But don't hit the gnat with a sledgehammer if you don't understand it, if you can do it by understanding it at a more fundamental level. Okay. And there's still another way. We could say, okay, well, let's see. Here we go. Here we have a graph of v versus t. At some point, our velocity is 30 centimeters per second, and our slope is negative 20 centimeters per second squared. So we want to find the run, rise divided by run equals slope, right? So run equals rise divided by slope. And there's a picture graphically. You need to understand all of that to understand what that cart's doing on the tabletop. Okay? They'll say that the cart on the tabletop doesn't really quite have uniform acceleration, but we haven't used the type of instrumentation you would need to verify that. Also, friction can be inconsistent, so you need a lot of data. You need a lot of trials to really get a handle on the slight nonlinearity of the frictional force. You need a very clean tabletop, and you need a good car. Okay?